Indeterminate forms and L'Hopital's rule. We're going to talk about indeterminate expressions, but before we start talking about indeterminate expressions, we're going to talk about something related, which is called an undefined expression. You see those a lot. This is the nefarious division by zero. But before we talk about undefined expressions, we have to talk about defined expressions. How are the real numbers defined? Well, the real numbers are a set of numbers, and they're defined to satisfy a certain set of axioms. There's two operations called addition and multiplication, and addition and multiplication have a bunch of properties that they satisfy. It's commutative, the order doesn't matter. These operations are associative, you can regroup parentheses. Multiplication distributes over addition, called the distributive property. So you can write as a times the sum of b plus c is equal to a times b plus a times c. And this is just part of the definition of real numbers, that they must satisfy this property. But in terms of undefined expressions, what's going to be really interesting to us are the definitions of 0 and 1. 0 is sometimes called the additive identity, or the identity element of addition. 0 is defined by this property. Any number x plus 0 gives you that same number x back. Similarly, 1 is defined as the identity for multiplication, or the multiplicative identity. It satisfies the property for any real number x. X times 1 gives you x. And also in the definition of 1, 1 is also not only defined to satisfy this equation, but 1 is a number different than 0. If the additive identity and the multiplicative identity were the same, that would actually lead us to some problems later on. So these are the definitions of 0 and 1. Also of interest to us will be the idea of inverses for each operation. So for addition, any number x, if you can find a number, which we write as negative x, or the additive inverse of x, an additive inverse satisfies this property. X plus the additive inverse will give you the additive identity, 0. Similarly, you can define inverses for multiplication. Again, x multiplied by its multiplicative inverse, which we'll write as x to the negative 1, that will give you the multiplicative identity, 1. Now, continuing on, one very common question is, 0 times x. We use this so much, we just think that 0 times x, we might mistakenly think that that's defined to be 0. But the definition of 0 has to do with addition. Combining the additive identity with a multiplication operation, well, that actually takes some thought. It's not an axiom, it's something we can prove. We can prove that 0 times x is equal to 0. And here's how you do it. 0 times x, well, first I'm going to rewrite the 0 in parentheses as 1 plus the inverse of 1, 1 plus negative 1 times x. Then I'll use the distributive axiom, which says I can distribute x through each of these terms. I'll get 1 times x and negative 1 times x. And then when you add those two together, let's see, well, first 1 times x, that's just x, since 1 is a multiplicative identity. You can also prove that negative 1 times x gives you the additive inverse. So x plus the additive inverse of x is 0. So we can actually prove this fact. It's a consequence of the axioms of the real numbers. And now we get to start to talk about undefined numbers. So what would the multiplicative inverse of 0 be? Well, if such a number exists, we know a couple of things. First off, the inverse of 0 has to satisfy this equation. By definition, 0 times its inverse must equal 1. But also, right up here, we proved that 0 times x is equal to 0. So at the same time, we should have 0 times anything. In particular, 0 times the multiplicative inverse should also equal 0. So let's put these two things together. If 0 has a multiplicative inverse, then, well, we know that 0 times a multiplicative inverse is equal to 1, but also anything times 0 is 0, which would give us 0 equal to 1. But back when we defined 1, we said that it's a number different than 0. So if this exists, we get a result which is not true. Therefore, our initial assumption that 0 has an inverse is false. You can't define the inverse of 0 in any consistent way. That's why we say it's undefined. It actually contradicts one of the axioms. Now, often, one of the things you'll show is that when a number has an inverse, a multiplicative inverse, you can calculate it as just the reciprocal of that number. And so that's why we often write 1 divided by 0, or the fraction 1 over 0. We'll also call that undefined. And this leads us to indeterminate numbers. So, what is 0 divided by 0? It's tempting to just say, oh, you can't divide by 0, so it's undefined. But you actually need to explain why this is true. So let's see if we can actually solve the equation 0 divided by 0 equals x. Let's see if we actually get a contradiction from this. Well, by definition, when two fractions are equal, that's true if their cross products are equal. So a over b is equal to c over d. You can check that by saying, does a times d equal b times c? So, if we say 0 divided by 0, let that equal x. Well, x can be rewritten as x over 1. So these two fractions are equal if their cross products, this numerator times this denominator, is equal to this denominator times this numerator. 0 times 1 equals 0 times x. And 0 times 1, we know that's 0. So, 0 divided by 0 equals some number x exactly when 0 times x equals 0. Now, that's actually not a contradiction. That's actually a tautology. That's always true for any value of x. 0 times x equals 0. We proved it. So here we have an equation with multiple solutions. And if your equation has multiple possible solutions, it's called indeterminate. You can't determine what it is without more information. To actually solve for x, it's going to depend on where 0 over 0 comes from. It depends on the equation which led you to this expression. And those equations usually involve some sort of calculus or limits. So, for example, let's consider the following problem. The limit as x goes to 1 of the fraction x squared minus 1 over x minus 1. Now, typically, when you're evaluating limits, you could break it up. You could do the limit of the numerator divided by the limit of the denominator. And then to evaluate the limits of each of these expressions, you just plug in 1. So plug in 1 up on the top, plug in 1 down on the bottom. You get 0 divided by 0. So that's an indeterminate number. We don't know what the actual limit is yet. So we're going to try something else to try to simplify to find the value of this limit. So instead, let's take the numerator. You might notice it's the difference of two squares. Let's factor that and then see what happens. You get x minus 1 times x plus 1 over x minus 1. So now, those cancel out. You're left with the limit as x goes to 1 of x plus 1. Now you can plug in x equals 1, no problem. You get 2 for your answer. So this limit is actually equal to 2. In this particular case. Now, that's not to say 0 over 0 is always equal to 2, just for this expression, 0 divided by 0 equals 2, for this specific limit. So, indeterminate expressions, basically they're expressions which have multiple possible solutions. Now, another place where these come from is expressions which involve infinity. Now, this can lead to great confusion. It often does. Because infinity is not a number. You cannot use infinity in equations. This leads to more misunderstandings than possibly anything else in math. Infinity is an abbreviation. It's shorthand for an idea or a property. That something which is, quote, equal to infinity, it just means that it's larger than any number that you could think of. So, for instance, sometimes you'll see people casually writing 1 divided by 0 equals infinity. That's not really an equation. That's why I put it inside quotation marks. But it expresses an idea. It actually expresses something about limits. This pseudo-equation really means that the limit as x goes to 0, 1 divided by x, this expression equals infinity. So there's kind of an implied limit here. But saying that something is equal to infinity, again, not quite right, because infinity is not a number. What this really means is that this expression, as x goes to 0, 1 divided by x diverges to infinity, which again is really just shorthand for something else. It means that as x gets really small, as it gets close to 0, the value of 1 over x becomes greater than any given number. And if you don't like these words, you can actually translate this into a series of equations. You can define what it means to be closer to 0, and that's actually the topic of an entirely different course called Real Analysis, making the statements in calculus really quite rigorous. Okay, so if you skipped over that part, the too long didn't read version, infinity is not a number. You cannot use it in equations. Often we'll write something like this to capture an idea. For instance, infinity plus 1 equals infinity. There's an idea behind that, but you can't use it as an equation. For instance, if you tried infinity plus 1 equals infinity, hey, let's just add negative infinity to both sides, and that cancels out, and that cancels out, and we're left with a 0 and a 0, and you get 0 plus 1 equals 0, so 1 equals 0, which totally does not work. We can't use infinity in equations. If we do, we're led to inconsistent, false statements. In fact, there's lots of indeterminate expressions that you could see, lots of things, which don't have a specific value. In addition to 0 divided by 0, there's infinity divided by infinity, 0 times infinity, infinity minus infinity, 0 to the 0, infinity to the 0, 1 to the infinity. All of these expressions could actually have multiple values, depending on the calculation or the context. And just as a brief, believability argument, each one of these expressions can be rewritten in terms of 0 divided by 0. So again, we're going to use this notation, 1 divided by 0 equals infinity. We're really just going to use that so we don't have to keep writing out limits over and over. But infinity divided by infinity, you replace these by 1 over 0, 1 over 0. You can write it as 0 over 0. Same thing for 0 times infinity. You do some math, and you can rewrite it as 0 over 0. Infinity minus infinity, again, these don't quite cancel out. You can use limits and rewrite this as 0 divided by 0. Slightly trickier, rewriting the exponential expressions in terms of 0 over 0. But it's the same idea each time. What we're going to do is say x is equal to 0 over 0. Okay, let's take logs of both sides. So ln of the left is equal to ln of the right. Simplify your logs and you get 0 times ln of 0, but ln of 0 goes to negative infinity. Again, there's an implied limit here. But 0 times negative infinity you could write as negative 1 over 0. And hey, you got 0 over 0 again. So ln x equals 0 over 0. You could rewrite x as e to the 0 over 0. And you can do the same thing down here. X is infinity to the 0. Take ln's of both sides. And do some algebra. You rewrite it as 0 over 0. Ditto for x equals 1 to the infinity. You can rewrite that, take logs of both sides, get infinity times 0, and eventually you'll get 0 divided by 0. So these are all indeterminate forms. 0 divided by 0, actually there's another way to see that this is indeterminate. You could rewrite 0 to the 0 as a limit in two different ways. But notice this top limit, x to the 0, well, anything to the 0 is equal to 1. And this bottom limit, 0 to the x, well, 0 to the anything is 0. And again, you get multiple possible valid expressions for this. It could be 1, it could be 0, it could be something else. So we're going to use L'Hopital's rule to help us figure out what those values could be.